Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we're going to discuss limits at infinity. The question we ask is, how do we compute a limit where x is going toward infinity? For example, consider the limit as x goes to infinity of x squared minus 1 over x squared plus 1. Recall that a limit exists if f of x can be made arbitrarily close to the limit L by taking x sufficiently close to a. That's the limit as x goes to a. But here a is infinite. So we mean by taking x sufficiently large. That is, does this expression x squared minus 1 over x squared plus 1, does it get close to some particular value as x gets larger and larger and larger? Okay, the way that we go about computing limits to infinity, and there are several, but this is the simplest one, is to look for the largest power of x in our expression. In this case, it's x squared. So we divide everything by x squared. We divide the numerator by x squared and the denominator by x squared, giving us 1 minus 1 over x squared in the numerator, 1 plus 1 over x squared in the denominator. Then as x gets large, 1 over x squared gets very, very close to 0. So in the numerator, it's the 1 that's the important term. In the denominator, we have the same thing, 1 plus 1 over x squared. The 1 over x squared gets close to 0, and 1 is the dominant term. So as we go toward infinity, as x goes toward infinity, the quotient becomes 1 over 1 or 1, and so the limit is 1. We might have to rationalize the numerator, or we might have to do some other trick in order to analyze the expression in order to find the limit to infinity, but this is a pretty standard approach. Okay, now let's discuss horizontal asymptotes, as these are related because here we're considering what's happening to the function f of x as x gets large to infinity or x going to negative infinity. We say that y equals L is a horizontal asymptote of y equals f of x if the limit as x goes to infinity of f of x is L, or the limit as x goes to negative infinity of f of x is L. What we're saying is, as x gets large, does the y value get close to something in particular? For the function in this figure, y equals x minus 1 over the square root of 4x plus 1, as x gets large, as x goes toward plus infinity, the value of the function gets very close to 1/2. And so we say y equals 1/2 is a horizontal asymptote. On the other hand, as x gets close to negative infinity, the y value gets close to negative 1/2. And so y equals negative 1/2 is also a horizontal asymptote of the function. Let's just conclude with some precise definitions. When a limit to infinity exists, we have let f of x be a function defined on a to infinity. Then the limit as x goes to infinity of f of x exists and is equal to L. What does that mean? It means that for every epsilon greater than 0, there is a corresponding number n such that f of x minus L in absolute values is less than epsilon whenever x is bigger than n. In other words, whenever x is large enough, the y value will be within epsilon of our limit L. That whatever epsilon we pick, we can go out far enough in x that x gets large enough so that from that point on, the y value minus our limit will be less than epsilon. That all y values from then on will be within epsilon of the limit. On the other hand, we have a definition when a limit to infinity is infinite. There we have let f of x be a function defined on a to infinity. Then the limit as x goes to infinity of f of x is infinite, means that for every positive number m, there is a corresponding number n such that f of x is bigger than m whenever x is bigger than n. In other words, if the limit is infinite, then no matter how large a number we choose, the y value will get bigger than that. So if we choose a big value m, we can always go out far enough in x getting closer and closer to infinity, such that the y values will always be bigger than m from that point n up to infinity forever on. Now let's take a moment for math culture. A police officer stopped a college physics professor for running a red light. The professor pleaded not guilty at his hearing and gave the judge a very eloquent explanation of how the Doppler effect, the redshift, could have fooled him into thinking the light was green. However, a student whom the professor had recently flunked pointed out the enormous velocity that would have to be reached in order to observe the redshift. So the judge revoked the red light violation and issued the professor a ticket for speeding. Thank you for joining us today. Have a great day, and may the power of math be with you.